I am the vice chairman of the Marconi Society, and I have the honor of introducing our next speaker, Irwin Jacobs. Irwin says, please don't read all of my biography, which I will not do because you can find it on the net, as was pointed out earlier. But I did think it was worth mentioning a few things. For one thing, he's the founding chairman and the CEO emeritus of Qualcomm. And if anybody in this room doesn't know Qualcomm, you've been hiding under a rock for quite a while. He was the founder of another company called Linkabit, and during that period of time, he was very helpful to me and Bob Kahn, who's here in the room as well, during the early period of the development of the internet, because he led the SatNet activities, sort of managed and oversaw that effort on our behalf at DARPA, and was very instrumental in getting that leg of the three-network internet up and running. He was at MIT as a professor. He wrote a book called Principles of Communication Engineering, which is still considered one of the best books on the topic. He's also well known for his public service. He's been chairman of the Board of Trustees of the Salk Institute since 2006, chair of the National Academy of Engineering from 2008 to 2012, on a variety of advisory boards and other things, and of course a Marconi Fellow in 2011, a well-known and generous philanthropist. So, Irwin, I hope that you'll forgive my brevity given the time of day, and I'd like to invite you up and thank you for participating today. So, Irwin, you're on.
Okay. Hi, everybody, and great to be here. Also, congratulations, Brad. It's very, very special. And I enjoyed that presentation, I think, as everybody else here did. There was a lot of information just unaware of. But I will add one more position location to your discussion. In any case, we had started Qualcomm back in 1985, July of 85, and started without any particular products in mind. Did come up with the idea of using CDMA fairly early on, but didn't have any resources to pursue it at the time. And so we moved ahead with another product called Omni. Not working? Oh, here's. Okay, should I start over again?
That's much better.
Right, very good. That's the only use for ties, and it failed. Otherwise, any case, we switched over to working on OmniTrax to bring that to market, and that was to be is a two-way communication system and position location for the trucking industry. And to keep the costs down, we're using geostationary satellites designed really for TV, although we also at Linkabit had developed VSATs for them, and that the VSAT world had taken off as well. But the problem was, how do you get a signal from a geo satellite to be able to receive and then transmit from a truck with a $50 antenna? And we did solve that with a very small antenna that could rotate and provide a fan beam in 360 degrees. Then the other question was that we had to use the full power of the transponder. How do we avoid interfering with everything else on the ground? And so we went to a spread spectrum signal, roughly a megahertz, and then swept it over the entire transponder bandwidth. Why? Because that's what TV signals did. And so we mimicked the TV signal to be able to know we would not be interfering with anybody on the ground, and indeed never did have a report of interference, so that worked out very well. But the next problem was, how do you get position location? And we started with LoRaN and put a LoRaN receiver in as well. And we got position location, not particularly precise, but every time somebody went by a gas station, which was quite frequently in the trucks, we'd kind of lose the signal due to some interference, et cetera. And so we decided that wasn't very adequate, and that's where one other position location approach came up, we had a very strong signal for communication to the truck that we obviously were receiving, getting communication information from that signal. And so what we did is we put a signal beacon signal on a second satellite with a reasonable number of degrees separation. That could be relatively narrow. We didn't have to use that much power because it was just a beacon. Then we had the problem, okay, we're listening to a communication signal. How do we, with one antenna, how do we get this other one? So we put in a scheme where ever so often we'd look over to where we expected to see the second satellite, make a quick measurement, and come back again. And so that was our position location, combined with a topo map, because we knew roughly where the truck was, we could end up getting good location. That system, we launched in the first commercial in 1988, and it operated for about 25 years successfully and profitably. I think it was the very first data communication, wireless data communications that actually was indeed profitable. However, once we sold it, launched it, ended up with now a cash flow, we began to focus in on using CDMA for the cellular industry, for the second generation of cellular, first generation analog, second generation digital. And we, at that time, GPS wasn't operational, but we were able to get the signals and use those to synchronize our base station. So we got a time signal and a frequency signal and use that for synchronization so we could get by with a cheap oscillator. And by the way, that's still being done. And keep the cost of the components down and help us do handoffs very much better. That decision almost cost the company existence because in order to convince people that we actually had a working solution for CDMA, we had to go ahead and build a demonstration unit. And there's a picture that you can see there. The little mobile phone required a van to drive it around, but that was okay. What we were trying to demonstrate was that we had solved the problems that people had said would stop CDMA from ever being used. And so we invited a group, not quite this large, but fairly large group, to San Diego to see this being demonstrated in November of '89, just 1 year after we began to look at CDMA for cellular. So a lot of effort getting that all put together. And I gave a presentation on the CDMA to everybody and was all set to say, okay, some going to a van, some going to the lab, here two sides of the conversation, when I had a wave from the back of the room, keep talking. Now, there are a number of advantages to having been a university professor. And one of them is you can keep talking for another 50 minutes. So I did. And luckily, about 45 minutes later, I think it was, had a wave to continue on. And actually, it wasn't until I was preparing this talk, I had thought that what had happened was that a GPS satellite came over the horizon with a bug in it and threw us off. It turned out, I then found out, that the receiver that we were using for GPS at that time failed. And so that threw everything off. We had to get another one going, get frequency and time reset up, et cetera, and they managed to get that done in 45 minutes, and Qualcomm might not have existed if they weren't able to move very, very quickly. And so GPS was right there from, in some sense, from the beginning with CDMA. Just a quick history there. We had that demonstration, took it to New York, because nobody believed that, yes, it might work in San Diego, but it'll never work in the canyons of New York, where signals get piped down the avenues and streets and give you lots of surprises, but it worked fine. We then had to go through a standards process, which was also a bit of adventure. I think one aspect of that adventure was that because it was code division multiple access, the NSA got somehow involved, and we had to convince them that it was okay. And we launched the first network in November of 95, so it's basically from 89 to 95, 7 years, or whatever that is, 6 years, 7, it's supposed to be. It was from 88 when we first started looking at it till 95 that we managed to get that to happen. Now there's one other thing I often mention when I'm here at or near Stanford, and that's that we, of course, when we introduced CDMA and everybody else was going with TDMA, there were a lot of discussions, arguments. There was a religious war for about 5 or 6 years as to whether the one or the other should be used. And there was an article in the Wall Street Journal front page that my hype might be costing the operators and some of the operators in the US billions of dollars because clearly this wasn't going to work. And they quoted a Stanford professor who said we had all kinds of problems. And then there was another Stanford professor that said CDMA violated the laws of physics. And so one of the things I do when I give a lecture here is I do point out that CDMA works now worldwide, except within a 5-mile radius of Stanford. Okay, so we had it launched, we went through the religious wars, but very quickly it became clear that one needed to be able to handle E911. That is, more and more people were beginning to use mobile phones, and how do you get a position location if there's an emergency? And there were a number of approaches to trying to do that. We very quickly focused on, because we were using GPS, on using a GPS in the phones. But of course, it turned out that there were lots of problems putting it into a small handset. First of all, of course, you're getting signals from a number of satellites all at a very low level and a direction that you originally weren't expecting. That the antennas really weren't designed for this, linearly polarized, no circular polarization, have to be multi-frequencies, et cetera, et cetera. And most of the cellular was FDD, that is receiving and transmitting at the same time. And so you had the potential of a huge jamming signal. So that all made life very interesting. But despite that, you wanted to have very rapid response. You wanted to have high accuracy. You wanted to use very little energy. You wanted to have it affordable and small. So it was a bit of a challenge. Well, we started working with a company up here in the Bay Area called SnapTrack. And they were working on augmented GPS, that is, using, which I think other aspects of GPS did, but using a server in the network to pass information to the mobile that would allow us to be able to integrate longer, to do a number of things that would allow us to actually receive the signal. One of which, by the way, the GPS signal, of course, does have information being communicated down about orbital information and clock information, timing. And the EB on N0 was typically much too low to be able to actually receive that in the handsets. And so that information had to be received at basically the base stations and in the network, and then passed over with this augmented GPS. And so then there was a long debate about which way to move ahead. You can see that graph that was done by people at SnapTrack with augmented GPS, with forward link trilateration, and then just by using cell IDs, and I'm not sure you can read too easily, but the accuracy on the bottom. And clearly, AGPS was desirable, so the CDMA, we went ahead using GPS and followed that. All of the other operators, the ones based on TDMA at the time, went ahead with the forward link trilateration, which didn't give you quite the accuracy and, of course, wasn't very reliable in rural areas where you did not have very many base stations. As a result of this, E911, the phase 2, which was specifying that you had to be able to get this type of location, specified less than 50 meters 67% of the time for 95% of the phones by 05, and I'll touch that a second. But for CDMA, that was a requirement. For the other technologies, they could get a factor of 2 forgiveness, so it was 100 meters rather than 50 meters. So ultimately, everybody, of course, went with GPS, but that wasn't the initial situation. The reason for taking time to get this installed, we had that in chips in 2001, and but there's a time to circulate the phones, get them all out there, people handing in existing phones, et cetera. And so until you get enough out there to get up to 95%, it took several years. But that all proceeded ahead rather nicely. One reason we're able to get, and I think Brad touched on this, but able to get GPS put into a CDMA chip quickly was that we already had a search function looking for pilots from the CDMA base stations, and we're able to use that to now search for signals from the GPS satellite. So it was a fairly quick adaptation of getting CDMA and of getting GPS in with CDMA. We had kind of a fun event there in 2002. Senator Clinton at the time was talking about how do you get business upstate, and so there was a meeting in Canandaigua and talking about E911 and the fact that you could now get that available on your cell phone. So she's come a bit of a long way since then. Some of us will keep our fingers crossed. Hopefully most. Any case, the whole issue then of the development of the chips, of Moore's Law, continuing to give us a lot of capability that we can put on a system on chip, and so more and more capabilities added. Brad mentioned that we're getting more satellites coming in from different groups. The dates are the ones when we had availability on our chip to support that satellite system. And so the number of satellites obviously is going up, and we are putting on the capability of supporting those, of course, using the assistance of getting information about each of those satellite systems from a server on the net, and getting that out to the handsets. And so we're moving very quickly toward being able to operate with 85 satellites up there. That, of course, gives you a lot of advantage, particularly in urban areas with canyons and things where you may not get good visibility, but it makes the whole thing more reliable and allows you to get access much more quickly. Well, what are we doing with all those extra transistors that we're getting on the chips? Among other things, we started out with, which was large at that time back in 2001 or so, with 10,000 correlators, and now we're in the million or more correlator region. So that allows you, of course, to correlate against the GPS signals much more rapidly. Sensitivity has been improved, even though one is now having to handle many more frequencies and share the antenna among many more uses. Power has gone down, always an issue, and I think if some of you use your mapping on your phone, you're often, at least I am, careful to disable the GPS when I'm not using it so my battery doesn't go down. But now we're getting to a point where we, in fact, can use other sensors to know when we're moving or when we're not moving. If we're not moving, you don't have to do the fix very often. If you're moving slowly, again, not too often. And if you're in a car moving more rapidly, then that's when you do a lot of rapid positioning. And the idea, of course, is that you can leave this on at all times. Interestingly, as you look to see what's being used now for position location, it's just about every capability that you put on the chip and in the phone, in particular, lots of different senses. So I'm not going to go through all of this, but clearly the application processor and the GPU are being used significantly, various types of DSP at low power, and then very special sections for doing the correlation, so you can get lots of correlators up there and not to use too much energy. The RF side gets to be very interesting because, again, of all these different frequencies, different uses, and so that's taken a large amount of effort to be able to do that and not self-jam. And then a lot of sensors coming in. Barometers mentioned there because now vertical height is getting important. If you're inside buildings and not getting too strong a signal, how do you check and track going up and down? And so that sensor is being used. And of course, all the other communication links that are available. So lots of different efforts being used to provide that position location in your handset. Why is that? Well, because position location, and there's only a small subset, of course, of the various applications, are being used in many, many ways. I think the picture for this conference was the one I should have had. It showed a large number of different applications, but they just keep moving along. Of course, great interest now in autonomous driving. That's putting requirements on position location. That can be very tight. We talk about less than a meter, and in fact, there's discussions of considerably less than that. Communicating between the automobiles, doing that with low latency, or even pedestrians and other objects, fixed objects. And so that whole area is putting a lot of pressure on how do we do this position location that much better. And drones, robotics themselves are moving ahead fairly rapidly. I was just a couple of days ago at a conference on robotics and smart robotics, and in particular in there, the various uses of drones, and those are, of course, rapidly expanding as long as we can get regulations that make sense, allow them to be used, but lots of different applications moving ahead here. And interestingly, all of them require a good location fix, and so good use of GPS. The other aspect often is these drones that they're flying around are also trying to build up their own worldview. Obstacles that they're going out, they might remember when they come back, if they're going out autonomously, being able to, again, remember the world around them. And so a lot of this information is being stored, and of course we're going to smarter type of capabilities, deep learning. So this is another way of taking a look, seeing the various pieces of information that are being combined together now on your little cell phone, to be able to make use of the various sensor information, be able to combine it together, again, use deep learning to perhaps augment the capability of doing this, and to get a good information about the pose of the vehicle or whatever it is that you're involved with. Still lots of efforts going into this. Again, new satellites coming into use, new capabilities, problems, how do we get location ubiquity, particularly indoor buildings, and that's getting to be an area of greater interest, so vertical accuracy. The battery issue, as I mentioned, lots of smart ways of trying to deal with that. The whole privacy issue comes up, and this fusion with more and more types of sensors, better and better sensors becoming available. So this whole area that Brad helped start is turning into quite an interesting experience and gives us lots of capabilities to use on our phones. Thank you.